All right, we're back. We're on page 177. We're going to talk about the final conic section. So we have degenerate cases, point, line, intersecting line. We have a circle, and then a little weirder is an ellipse, and then a little weirder is a parabola, which we're going to talk about. And then finally, the weirdest one is hyperbola, which we already talked about. So parabola is the final one we're going to talk about. I don't know why I put them in the order that I do, except I feel like an ellipse and a hyperbola are so similar that like you might as well learn them like back to back. To me, that makes the most sense. Let's talk about a parabola. You actually know a lot about parabolas, or you've at least worked with them a lot, because the quadratics, like quadratic formula type stuff, use that on basically parabolas. So let's see, the definition of a parabola. Parabola is the set of all points in a plane that are equidistant from, I don't like my thing. So what am I doing here? Equidistant from a point, which is the focus, and a line, which is called the directrix. So it's a set of all points in the plane that are equidistant from a point, which is the focus, and a line, which is the directrix. So there's a bunch of stuff that we're going to learn about them. What I want to do is I'm going to switch over to GeoGebra for a second so that you can like see what that means, because I think it's like hard to visualize. So this is that little GeoGebra book that I threw together. If you go to parabola, equidistant, point to line, it'll open this up, and then you can kind of, so here's the focus. This is the point that every point on, this is our parabola. Every point on this parabola is equidistant from this point, which is the focus, and this line, which is the directrix. So if I take the point and I kind of move it, you can see there's always kind of this isosceles triangle here, which actually when you're creating one geometrically, there's another video of that. You should definitely watch it, see if you can do it. When you're creating it geometrically, that is crucial. So we have this, and I encourage you, find the video of how to make one and actually try to make one. I can move the focus a little bit. And so we can move this, and it's always equidistant between the point and the line. That's the definition. It's hard to envision, I think, but once you see it, you're like, oh yeah, now I kind of get what that means. So there's actually a couple of important points. One of them is this point where it currently is. So you see, I'm moving horizontal to the directrix, right? So the directrix is down here. From the focus, I move parallel. Parallel is the word I'm looking for. I move parallel, and eventually I hit the parabola. So that's one endpoint of a very important segment. And then over here by symmetry, there's going to be another one, right? Those are called the endpoints of the lattice rectum. So the lattice rectum is probably the funniest name associated with conics. It is the segment that passes through the focus that is parallel to the directrix. The length of it, right? So from this point to this point is called the focal width, because it's the width of the parabola through the focus, right? There's a lot of widths. Like if I just go from kind of like where the cursor is right now over to here, like that's a width. If I do it here, that's a width. The focal width is the important one. So that's the distance from one side of the parabola, I guess, if that's a thing, to the other side of the parabola passing through the focus, focal width. And then there's one point here when you're moving perpendicular to the directrix. So through the focus, perpendicular to the directrix, the midpoint of that segment is the vertex of the parabola. But you already knew that because everything you've ever done with parabolas so far has probably involved like finding the vertex. So we have a vertex, we have a focus, we have a directrix, we have one endpoint of a lattice rectum, we have another endpoint of a lattice rectum. These are a lot of the things that we're gonna have to find. So we already know the eccentricity is 1 because we have to memorize that. And then the focal width is gonna be the length of the lattice rectum. We're gonna list that also. So let's go to the notes and see what we can do. So back to the notes. So these are these, I don't know, I say all of them are pretty simple. The parabola is a little weird, right? Because you have experience with it, but that's good, right? So we're gonna look at ones that open up, down, or left, right. And you kind of already know what's happening. So if you see x squared, think of everything you ever did in algebra. It opened up and down. So if x is squared, then it opens up and down. If x is not squared and y is squared, it's going to open left, right, because it doesn't open up, down. And those are the only two options. So that's literally how I remember that. So here we go, some things. If you're going to open up, down, then you have a vertical axis of symmetry, right? So this is kind of your axis of symmetry. It goes through the focus and the vertex. We have a vertical axis of symmetry. We have our focus. Well, let's look at the equation. It's y minus k equals, now the weirdest part, 1 over 4p. Unquestionably the weirdest part, 1 over 4p. And then we have x minus h squared. So a parabola doesn't have a center, but like everyone kind of feels like the vertex would be the center. And it turns out that the vertex is hk. So this point right here is hk. And now if you, let me tell you what p is. So p, well, actually, do I know what p is? I'm not really sure. Well, I know what p is. P is the distance from the vertex to the focus. So I don't know why it's called p though. So this distance is p. And then by symmetry, this distance is also p, which means that this distance is 2p. And then, because of the way it works, right, we know that, hold on, I'm adjusting the width of this highlighter. We know that the distance from the focus to the parabola and the parabola to the line is equal. So this must also be 2p, which means a bunch of things. It means that the focal width, I don't know why I've decided to do all this in purple, is 4p, and that is our focal width. And then you can get like a lot of coordinates out of what we've written so far, right? So this point is hk, and if I move down p, I end up at the directrix. So the directrix is a line, and in this case, it's a horizontal line. So I'm going to say that this line is y equals k minus p. And then this ordered pair right here is going to be, well, first let's figure out the focus, right? The focus is h comma k plus p. So then this must be h plus 2p comma k plus p. And like in practice, you don't write them out this way, but you want to think about it, right? So like we'll have a number and we'll be like here, and we'll know that p is 2, so we'll like move up 2, and then we'll move over 4, and then we'll know this coordinate, and so on. Like you know values when you're doing this. It's not as general as we're making it, but this point is also an endpoint of the lattice rectum, so it's h minus 2p comma k plus p. I get a lot of problems wrong because I accidentally used the vertex. Like one of my more popular videos, I think I actually did that. So watch out for that. I do it wrong all the time. When you're finding the endpoints of the lattice rectum, you got to go through the focus. Like it's the focal width, right? The focus is involved, but I messed that up. So if you're going to open up, so if it opens up, then 1 over 4p is going to be greater than 0. If you open down, then 1 over 4p is going to be less than 0. But you already know that, right? Like if I gave you y equals, if I gave you y equals x squared, right? So 1 over 4p is 1. And you know that y equals x squared opens up. If I gave you y equals negative x squared, then 1 over 4p is negative 1. And you know that negative x squared opens down. So you already kind of knew that stuff. So what else we got here? Over here, same deal. So can we like mark it all up? So the key thing is what's being squared. So for this, see that it's y being squared, so it opens left, right. Over here, I saw that it was x being squared, so it opens up, down. These are things that you need to know. That's like actually probably the most important thing in terms of like quickly identifying stuff, I guess. I don't know. Our vertex is hk. All right, so we know that we move p units to get here, so it's going to be h plus p comma k. We know that this we're going to move up 2, so it's h plus p, and then k plus 2p. Here we're going to move down, so it's h plus p, k minus 2p. So all of this is kind of predicated on the fact that this is 2p, this is 2p. So the focal width is 4p. These are the endpoints of the lattice rectum. Here's one endpoint. Here's another endpoint. Oh, somebody forgot to put a parenthesis there. Probably me, hard to say. And then our directrix, in this case, will be a vertical line, so it's x equals something. What does it equal? X equals h minus p. So the up, down, opening up, opening down, like because it's so ingrained in your brain, you already pretty much knew that. Here, if 1 over 4p is greater than 0, you're going to open right. And I always think you open toward the positive x-axis. Like if positive goes positive, negative goes negative. If you have 1 over 4p less than 0, you're going to open left. All right, so let's see what I forgot to say. And then we'll pretty much be done with this page. So you already know the up-down thing, positive coefficient. Yeah, so this is like a thing in math, actually, that you kind of have to get used to. But like positive coefficient means up or right. And then a negative coefficient means up or right. The positive coefficient means up or right. Positive coefficient. I never said what negative means. So negative means left or down. That's the opposite. That was weird that I didn't clarify that. The focus is p units from the vertex along the axis of symmetry. The directrix is p units from the vertex, and it's a line. It is a line. That's the biggest mistake I see people make when they know what they're doing. We got a focal width. So what color am I using here? Focal width is 4p. Focal width is always positive. So it's 4p. And you go 2p in either direction from the focus, pretty clearly. And then the formulas that I've written are actually different from what you'll see in textbooks. Most textbooks bring the 4p over. They'll like multiply both sides by 4p. So it'll be 4p quantity, and this will be gone. I don't like that because you've already learned so much about them. So that's why I don't do that. So 7 things. This is the big deal. 7 things. You're going to do equation, vertex, focus, directrix, endpoints of the lattice rectum, the focal width, and the eccentricity. So it's like it's a very different set of things, I guess, because the directrix is new, the lattice rectum is new, there was no focal width before, eccentricity still there, but you haven't memorized. So parabola, just set of all points in a plane that are equidistant from a point and a line. It has definitely the most different definition of all of them, but I'm going to come back in the next page, do some problems. So I will see you there.